This video demonstrates the progress made on the second version of the Space Combat Simulator. Here you can see the player ship, the model for which I did not make, a basic HUD, and a few asteroids, which are marked as triangles on the HUD. Currently we're modeling basic flight controls, including yaw, pitch, and roll. To help depict the player's movement, we can activate a 3D grid of fixed points on the HUD. Notice how the movement of the ship is not affected by its facing, as this simulator uses Newtonian physics. We also have different camera modes, including a drop camera, which remains stationary and tracks the player, as well as a flyby camera, which predicts where the player will be in 2 seconds, goes to that point, and then tracks him until he flies by 1 second later. Other objects in space are marked by indicators on the HUD. They can also be located by activating the radar display in the lower left of the screen. The radar depicts a flat 2D plane viewed from an isometric angle with the player at the center. The objects above and below the plane are plotted by a vertical pole connecting their radar blip to the 2D plane. The length of the pole indicates their height above or below the player's two-dimensional plane. When a radar contact is targeted, the blip it's associated with doubles in size. Watch as several radar contacts are cycled through. Notice when we target the asteroid in front of us, the white triangle surrounding it changes to a green box. The player now turns to the right to put the asteroid at its 9 o'clock position, then rolls to the left to put the asteroid directly above him, and then pitches down to put the asteroid at 6 o'clock. Currently the only modeled weapon is a homing missile. The missile has 4 stages: an initial phase, where it flies straight until it gets 10 meters from its launcher before arming; then a chase phase, where the missile turns directly towards the target and accelerates until it has a positive rate of closure. The third phase is the intercept phase. The missile's facing is determined by the relationship of several calculated points. First, we calculate the time until impact based on the distance to the target divided by the rate of closure. This changes as the missile continues to accelerate, but is still accurate enough for this purpose. The calculated point of impact is predicted by plotting where the target will be at the time of impact. Next, we plot the projected path of the missile, which is where the missile will be if it continues on its current vector until the time of impact. Currently, the calculated point of impact and the projected path of the missile are separated. To achieve a hit, we need to bring these 2 points together. To do that, we need to plot a missile aim point. The missile aim point is calculated by drawing a vector from the calculated impact point to the projected path of the missile and then reversing it. As the missile guides in on the aim point, it changes where it will be at impact time. This brings the missile flight path and the calculated impact point closer together, which in turn brings the missile aim point closer to the calculated impact point. When all 3 points are within 100 meters of each other, the missile switches to the terminal phase, switching off the main thruster, pointing directly at the target, and using small lateral thrusts up, down, left, and right to adjust its path before it impacts. In the terminal phase, if the missile thinks that its projected path and the impact point are within 10 meters of each other, it reignites the main thruster and accelerates until it runs out of fuel.